we're going to take a first look at a combined loads problem. So combined loads meaning we have more than one load acting and from which we want to calculate stresses. So in this problem we have a cantilever beam of length L and we want to find the stress at point A at the top of the cantilever beam as a result of the combined loads. So the combined loads that we have, we'll underline here, we have an axial load P, which would be pulling the beam in tension, and then we have a shear load V acting at the end of the beam. We're interested in this stress at this point A. So one thing to note is that V, if we look at this figure on the right here, which presents the cross-section view, you'll notice I added some coordinate systems here and here just to make sure we understand what we're looking at. But V is acting through this midplane of the width, so it's not adding any torsion to the problem. So the two loads we have are P and V, but we're not twisting the beam at all. If V were acting over here at a corner, then you'd have some added torsion from V. But yeah, we're not going to deal with that one for now. So the first thing we want to do if we're trying to find stress at A is we need to make a free body diagram. So if we were to make a cut right here, pretty much right at the wall, and were to redraw the forces that we have acting, then we'll be able to see what the stresses are a little more clearly. So what I'm doing is redrawing. So I've made this cut here and redrawing the beam. So I know I have an applied load P and we have an applied shear load V. So that means that this cut that we just made, there has to be a reaction P also in the axial direction, and there has to be a shear reaction V as well. And we'll remember that we're looking for stresses up here at the top of the cantilever beam. Now let's also remember that there's going to be a reaction moment, right? So that V pointing downward at the right hand side is going to give us a moment, a reaction moment that will be doing this, right? So in our coordinate system this would be a moment about the z-axis. Okay, so now what we'll do, that we have our coordinate system, we'll take this point here and we'll draw a stress element of the stresses that an element at that point would be seeing. And what's nice about the way that we've done our free body diagram, if we're looking over here at the loads acting on that point, you'll notice we have this shear V. That shear load V is pointing up, so we know we have some shear loading. So well, we could have some shear stress, and then P is pulling that direction on the beam. So we have some tensile loading from the tensile load P. And then you'll notice, I drew an arrow P on the opposite side just to balance the forces on this element that we have here. Same with the shear, I drew an upward shear, and then we know that to balance that shear load, you have to have a shear on the top face with the arrow pointing towards this other arrow on the left face, and then with arrows on the opposite side to prevent any rotation, we also have to have these other shear stresses on this element. So that's why I'm adding these extra forces, just because it's all balanced. So this is as if we're drawing a free body diagram around this element at the location we're interested in. Okay, and then let's not forget the moment. So this moment, the way it's bending the beam's going to take a shape. If I draw up on the top, I'm going to draw in red, but the beam, because of bending, and this is exaggerated obviously, but it would take a shape like this. Okay, So we know that this moment is adding tension to the top surface, right? So it'd be adding tension to this entire top surface. And that's where this point A is. So we know that there's going to be some added tensile loading at this point A from bending as well. Okay, so I'm actually going to erase that P for a second. What I want to do is just directly write in the equations for the stresses that we see. So we know we have a tensile load, which is P over A, and that's causing tensile stress. We also know we have added tension from bending, and the stress from bending we've learned is MC over I. Okay, and then the stress due to shear, it's tau, and let's just remember what coordinate we're looking at. So this would be tau xy, since when we look back up here, it's acting on the xy system. We have tau xy, and we know the equation for transverse shear is VQ over IT. Okay, so those are all the stress states that we'll have from this combined loading. Now we need to go and figure out what each of those terms is, and we'll add them up. So you'll see here we have two tensile stresses, so those will add up to give us one tensile stress. And that's in the x direction, right? So we'll have a sigma x. That's the combination from the axial load and the bending load. Okay, so let's go through and get each of these. So let's start with the shear, because we'll see that one's actually easy here. So tau xy, the equation is tau xy equals VQ over IT. Now this one we can jump right ahead, and we already know what it's going to be, because let's look back up at our diagram. But remember that shear stress, when we're looking at the surface, is going to be 0. And you'll remember that because Q at that top position, if we're looking here, you'll remember that Q is equal to the integral of y dA prime, with dA being the area above the point of interest where you're finding shear stress. Well, up at this top surface there is no area above that point, so Q is just equal to 0 at the point that we're looking at. So we're going to end up having a shear stress equal to 0. Okay? So 0 shear stress for this specific problem. So let's move on to the tensile stress. Okay, so we have two tensile stresses. So we have the tensile stress from the axial load. So let's just write out what we know we have. We have an axial tensile stress, and that is equal to P over the cross-sectional area. Oops. P, because that's our, if we look back up at our diagram, P right here is our axial load. And then our cross-section, again looking back up at our diagram, is just this area B times H. Okay? So let's fill that in. So we have P over BH. That's our stress due to the axial loading. We also have tensile stress from bending. And we know that that is equal to MC over I. Let's remember C. I'm using C here instead of Y. C is what you use when you're looking for the stress at the outer surface, the surface furthest away from the neutral axis for a symmetric beam. So C is the same as, instead of using Y, C would be the max distance, which we know in this case is going to be half of the thickness. So if we were looking at our neutral axis of this beam, it's right through the middle since it's a symmetrical shape. And it's a straight beam, so C in this equation will be h over 2. So that's half the thickness. The moment is caused by this force V acting over this distance L, right? So we have a moment of m times L or V times L. So that's m. C we said is h over 2. And then I, the moment of inertia, you'll remember is, just a little bit. I, we won't rederive, we'll just write is bh cubed over 12. Okay. And after doing the algebra, this quantity is going to simplify to 6 V L over BH squared. Okay? So from this combined loading, like we said, there's no shear loading at point A. All that we have is stress in the x direction. So this would be what our stress element looks like as a result of combined loading at point A. And then our expression is just the sum of the two tensile stresses that we just found. So that's P over BH plus 6VL over BH squared. Okay, and so that's the stress that you have from multiple loads acting on this element. So you can see there's two stresses causing tension. So the tension at that element and those tensile stresses, the loading is in the same direction. So these two tensile stresses are going to add together, and this will be the stress from that combined loading.